Today, I want to talk to you about an exciting development in space science. Astronomers from MIT, NASA, and other institutions have discovered a new way to measure how fast black holes spin by using the flickering results of a stellar feast. Let me explain. A black hole exerts a tremendous tidal force on a passing star, tearing it apart. Part of the star is flung into space, while the remaining part forms an incredibly hot disk around the black hole. This hot disk holds the key to calculating the black hole's spin rate. The team led by MIT has shown that by examining the wobbling of this newly formed disk, we can determine the spin speed of the central black hole. According to a study published in Nature, astronomers tracked the pattern of X-ray flares produced immediately after a black hole undergoes a tidal disruption event. They found that these flares, observed over several months, likely signal a bright, hot accretion disk being pushed and pulled by the black hole's own spin. By tracking how the disk's wobble changes over time, scientists could calculate how much the disk is affected by the black hole's rotation and thus how fast the black hole itself is spinning. Their analysis showed that the black hole spins at less than 25% of the speed of light, which is relatively slow for black holes. MIT research scientist Dheeraj D.J. Pasham, the lead author of the study, says this new method could be used to measure the spins of hundreds of black holes in the coming years. If scientists can study the spins of many nearby black holes, they can start to understand how these gravitational giants have evolved over the history of the universe. The study includes collaborators from NASA, Masaryk University in the Czech Republic, the University of Leeds, Syracuse University, Tel Aviv University, the Polish Academy of Sciences, and several other institutions. Every black hole has a natural spin shaped by its cosmic encounters over time. For instance, if a black hole has grown primarily through accretion with material occasionally falling onto the disk, it can reach very high speeds. Conversely, if a black hole has grown mainly through merging with other black holes, each merger can slow down its spin as their spins align or misalign. As a black hole spins, it drags the surrounding spacetime with it. This dragging effect is an example of the lens-throwing precession, a long-standing theory that describes how extremely strong gravitational fields like those produced by a black hole can twist the nearby space and time. Normally, this effect isn't apparent around black holes because these massive objects don't emit light. Physicists have suggested that in events like tidal disruption events (TDS), scientists might have the chance to track the light from stellar debris as it gets dragged around. This would allow them to measure the black holes. During a TDE, scientists specifically expect that a star can fall into a black hole from any direction, creating a disk of white-hot, fragmented material that might tilt or misalign with the black hole's spin. Imagine the accretion disk as a tilted donut orbiting around a donut hole with its own separate spin. Varsailin-Matin, as the disk encounters the black hole's spin, it wobbles while the black hole tries to align it. Eventually, the wobbling diminishes as the disk settles into the black hole's spin. Therefore, scientists predicted that ATDE's wobbling disk should be a measurable signature of the black hole's spin. Pasham notes that the key was having the right observations. To achieve this, one needs to continuously monitor a tidal disruption event with a telescope for a long period, from the initial moments to several months. Over the past 5 years, Pasham has searched for tidal disruption events that are bright and close enough to quickly track and monitor for signs of lens-throwing precession. In February 2020, he and his colleagues got lucky with the detection of at 2020 a bright flash emitted from a galaxy about 1 billion light-years away, initially detected in the optical band by the Zwicky Transient Facility. The optical data indicated that the flash was from the initial moments following ATD, given its brightness and relative proximity. Pasham suspected it could be an ideal candidate to search for disk wobbling signals and potentially measure the spin of the We needed fast and high-cadence data, says Pasham. The key was to catch it early because this precession or wobbling should only be present in the early period. Later, the disk would no longer wobble. The team discovered that NASA's NICER telescope could capture the TDE and continuously observe it for months. NICER, which stands for Neutron Star Interior Composition Explorer, is an X-ray telescope located on the International Space Station that measures X-ray radiation around black holes and other extreme gravitational objects. Pasham and his colleagues examined NICER's observations of at 2020 over 200 days after the initial detection of the tidal disruption event. They discovered that the event emitted X-rays that peaked every 15 days for several cycles before. They interpreted these peaks as moments when the TDE's accretion disk wobbled, facing NICER's telescope and emitting X-rays directly, then wobbling away while continuing to emit X-rays similar to waving a flashlight towards and away from someone every 15 days. The researchers took this wobble pattern and applied it to the original theory of lens-Thirring precession. Based on estimates of the masses of the black hole and the disrupted star, they were able to estimate that the black hole's spin is less than 25% the speed of light. The results show that scientists have used observations of a wobbling disk following a tidal disruption event to estimate a black hole's spin for the first time. With new telescopes like the Rubin Observatory coming online in the coming years, Pasham anticipates more opportunities to detect black hole spins. The spin of a supermassive black hole tells you the history of that black hole, says Pasham. Even if a small fraction of those Rubin detects have this type of signal, we now have a method to measure the spins of hundreds of TDS. Then we can make a grand statement about how black holes have evolved over the lifetime of the universe.